I want to talk about debugging today because debugging is a pretty important topic. I spend a lot of my time debugging, unfortunately maybe, because as Chandler just said in his talk, our software inevitably contains bugs. And I say this in a slightly less nice way. We all can't program correctly. So we make bugs, and then we have to make sure that we notice when our application has bugs, that we find those bugs, that we fix them, and then possibly that we avoid making that same bug again and again. So who is this talk for? This talk, as one of the reviewers said, is somewhat of a training talk. So if you're more new to C++, this is definitely the talk for you. But it's hopefully useful to a wider audience. And as somebody said who had a bit more experience, that my talk was a good reminder of how they should do things. And apparently they did not. Okay, so when we talk about debugging, we have to get some definitions out of the way. We can say that the programs we write have some kind of specification. Typically, that specification is somewhat implicit. Maybe parts of it are written down, but large parts of it will be just shared in the minds of you and your teammates. Unless you work in some area where you have more stricter validation requirements, then probably more things are written down. Now, our program has a bug, of course, if it doesn't conform to that specification. But what we receive typically are just bug reports. So reports that describe a symptom of some misbehavior, and they don't describe the actual bug. We have to find where the mistake is. So the first step in that journey of writing better software that is bug-free as far as that is possible is that we want to get as many bug reports as possible. So this is a bug report. You see, this is an email I received 15 years ago, and I remembered it until I wrote this talk, because it is not a very good bug report. It's very short in details. Also has some attitude issues, maybe. But I remember I could help that person. That's what counts. We have different ways, and we have many different ways of noticing that our application contains bugs. It might just crash or dump the core. We might get an error message. Maybe we write something to a log file, something unexpected maybe, or the application misbehaves in some other observable way. And we want to notice as many of them as we possibly can. And most importantly, we want to notice them when these happen on a client's machine, for example, and not on our own developer machine, where it's easy to see that. So we want to increase the number of bug reports that we get. That's our first mission. So luckily, we are writing code in C++, so we have, as the first line of defense, so to speak, we have the compiler that does type checking, that prevents a few bugs. We can help the compiler a bit with static asserts, or maybe we can calculate more stuff at compile time, and that eliminates an entire class of bugs. So who knows what this eliminates when we do compile time evaluated stuff? UB, exactly. There was a talk at CppCon of people who did, I think, their entire microkernel to prove that this was UB free. Now, after compile time, we can still do more testing. We can do automated testing. We can do unit testing, hopefully. But that will still leave a lot of bugs in our application, bugs that we can only find at runtime. So what can we do at runtime? So at runtime, we at ThinkCell at least, we do very strict error checking. That means we check all the API return values from all the functions we call, and we distinguish between expected and unexpected return values. So, for example, if you're trying to open a file, it is probably always an expected case that that file does not exist. That's a case that you will probably have to handle. It would be very surprising if create file suddenly returned error out of paper. And if it ever did, I certainly want to know and want to investigate this. So error out of paper is a bug that would, a return value that would be reported. We also write a lot of asserts to assert preconditions and postconditions, and these asserts stay in release builds as well. And these will also report to our backend if they fail. And in this way, we try to enforce a lot of invariance. We try to make sure that our application, our program, stays on that path of behavior that we intended and that we expected. And as soon as it derives from that path, it should send us a bug report. So there was an entire talk by my CTO, Arno, about this last year here at CppNow, if you're interested in more details. From my point of view, this looks like this. So we have some database where all these bug reports from all those users come in, and where I can analyze them and look at which are the most frequent ones, on which systems do they occur, in which environment, which version of our software. I can filter them. I see the line of code where they happened, etc. So this is extremely useful to get notified of bugs that maybe depend on some specific environment, bugs that we could never reproduce in-house. They only occur if you have some other software installed, which is weird. Okay, now let's say we get as many bug reports as we possibly can, partially automated, like we've just seen. Now we want to investigate that. We want to find out what's the cause. We want to fix that bug. And maybe there's a bug that's appearing on a colleague's machine, and you don't know anything about it. You don't know if this is ever again reproducible. You don't know what he did. You just know it happened now. Maybe that colleague calls you over from the testing department and says, hey, can you look at this right now on my machine? So is it worth it having such a process in place where maybe your team is organized in a way that you can just come up to somebody else and say, hey, I have a bug open on my machine. Do you want to look at it, without knowing anything else about it? And I would say that's a very, very good idea. It can often be the only way to find a bug. So there's this famous quote, 1 in a million is always next Tuesday, by the architect of MS-DOS 4. And what he meant by that was that by then, computers had become so fast that every situation that had only a chance of appearing of 1 in a million would probably occur by next Tuesday. And here, when we have a bug that we don't know anything about, this might be our lucky Tuesday if we analyze it, even though we know so little. It might be that this is our rare chance to analyze a bug that is super hard to reproduce in the lab, yet it would have an obvious fix if we just stared at the code and actually thought about it for a moment. But we can be pretty sure that once we roll out our software to millions of users, that rare bug that we cannot reproduce will occur thousands of times. So maybe it's better to invest some time early without doing a large, and further analysis. So what can you do in that moment? And at the very least, you can form an hypothesis on the cause of that symptom. You can look at the code, you can look at the situation the program is in and wonder, how could that happen? And maybe you can form some hypothesis and then test them in code. Can that happen? But in some rare cases, this is actually our only chance of fixing a bug because the bug is inherently hard to reproduce. So we have our first little quiz. That's the interactive part. I brought my best bugs, all the bugs that could fit on a slide. So let me explain what we're doing here. We're trying to do some HTTP requests. And the asynchronous API, whatever, requires that we have some delegate object. This delegate object will be called when new data is available. And then it will lock a mutex. It will set its state, depending on if the HTTP request was successful. Then that state is data. Otherwise, it would be error. And then we do something with the data. So the exacts, what we do with the data isn't so important here. Then we release the mutex, and we notify our condition variable. But now in that case, we're pretty lazy. We're actually doing that HTTP request synchronously. So what we're doing here is we're checking that unique lock on the mutex, and we're waiting on that condition variable. We want to wait until the delegate has something for us, either an error or data. And then when we find out it has an error, then we just throw an exception. So this is subtly wrong. And this will run. It will run for a very long time. But like once every few weeks, it will crash here. Why? So this is inherently not reproducible. We could never reproduce it. But we had to look at it and wonder, what did we do wrong? Any ideas? It's also violating a C++ guideline, which would fix the bug. Can you all read it?
It's a little hard.
It's a little hard. Ah, that's too bad.
I'm assuming the scope of the lock is fine.
The scope of the lock is, well, maybe not. But where is it wrong?
Is the lock in the Lambda will be unlocked all the time when we are returning on the right side?
Here?
Yeah.
No, we will hold it when we return, right? When we return from the wait, we will get the lock, or we will have the lock. I think that is correct. Well, and so what could cause that to crash? MCV is not there anymore.
If the delegates throws and was destroyed by the time we get to notify all.
Exactly. This has thrown. But how could that throw? How could that throw when we had a mutex and everything? Spurious wake-ups. So this actually happens. So the problem here is that we are releasing that mutex here before we do the notify. We've already set the state that we're waiting on there. We haven't notified yet, but now we get a spurious wake up, and this code will run, and it will throw, destroy the delegate, and when that guy here continues, he will crash here. So this actually happens. This happened in our HTTP server, every few weeks, and the solution is to put the notify into the mutex, which is what the CPP guidelines recommend for that reason. Okay. I have another one in that category, which has less to do with C++. So we have some shared temporary file. It's like a block of data that different processes can append data to, and they can only append data in a single block. And they can read out of those blocks. And they can mark one of those blocks as deleted, which at first just means we set a flag. And later, if some other process comes along and wants to append more data, we might compact the whole data structure. And now the bug was that some process came along and said, well, I'm reading data, but that's in a corrupted format. So something went wrong in that whole data structure. So that has only 3 operations. We can append data to the end, which means we take an exclusive lock on the file. Then we compact that data if necessary, append data to the end, and return a handle to that data. We can read, then we take a shared lock on the temp file, and we copy data out. And last but not least, we can delete one of those handles. We also take a shared lock, because at that moment, that only means that we set a flag. Now, same question. That was wrong. It was hard to reproduce, but it was occasionally wrong.
So delete should happen with the exclusive lock, right? But we are taking shared lock for deletion.
In general, yes, but since I'm only setting a flag here, not actually changing anything, the shared lock is fine. But of course, it has to do something with the logs, because that's all there is. But what? Yeah?
Is the lock in shared memory?
The lock is not in shared memory, but it is on the file. It is an actual file log. So file logs have one weird property, or maybe not so weird, if you know. So are file logs a good synchronization mechanism for processes? They are a good synchronization mechanism for processes. So if one process takes that exclusive log, no other process can access that file. But different thread from the same process can. So they only exclude other processes. So if you have suddenly different threads doing the same thing, then that won't work. And I think that's at least on Windows, and I think it's everywhere. The file log is a property of the process. So that was the same category. It was a bug that we couldn't reproduce. We could just go back over all the assumptions we had made and then ask ourselves, were these assumptions actually valid? Or did I make a mistake in my thinking? Okay, typically we're not so lucky. Typically it's not enough to stare at the code and wonder what the problem is. We need to do some more analysis. So this is an iterative process where we get a bug report, then we analyze it a little bit. Maybe we form an hypothesis what the problem could be, we test that, and then we are probably wrong on the first try, and we keep doing that until we find the actual problem and we can proceed to fixing it. And it's important to do this right and not to jump to conclusions or to narrow down your hypothesis too early. And it's also very important to keep at it, because this can often be very frustrating if you have a bug and you have no idea what could cause it. But there is typically a solution. Those mysterious Heisenbugs rarely exist. It's just that maybe the system is too big for us to analyze. But there would be a solution. And in order to analyze that bug repeatedly, of course, first we have to reproduce that bug. And now, reproducibility of a bug, that's not a binary property. A bug is not either reproducible or not reproducible. But there are a lot of shades of gray here. So in the best case, you have a bug that is always reproducible on any machine you try it on in a debug build. And then it's relatively easy, let's say, to find the cause. But we can go down here and maybe, in the worst case, that issue is only sometimes reproducible, only in release builds, maybe with very specific optimization settings, and only on very specific machines. And in those cases, it will be very hard to find the actual bug. So we want to move up here. At first, we want to make sure that we make that issue more reproducible. And there are a few techniques that we have to do that. So if our bug is only sometimes reproducible, then there are first, of course, a couple of tools that hopefully most people already use that make hard to reproduce issues easier to find. So the address sanitizer, the thread sanitizer, and the undefined behavior sanitizer, for example. And especially the address sanitizer is super useful in finding all the bugs where you use variables after they've been destroyed or freed, etc. So does everybody who uses the address sanitizer regularly? That is not as much as I expected. Who does not know, or who knows, let's ask that way, who knows what the address sanitizer does? Okay, so the address sanitizer will instrument your code. It will add instructions to your code. And it will make sure, it will actually, track the memory you've allocated and freed. And it will tell you when, for example, a temporary variable has already been destroyed, but you're still accessing it because you have some reference, some dangling reference. Typically, this will very often work. When the memory has not been changed yet, you will just access the old out-of-scope variable. The data is still there, everything works. But it's a bug waiting to happen. The address sanitizer changes the memory pattern and will then tell you, hey, this memory has already been cleared and you have a bug here in the code. So if bugs are only sometimes reproducible, it can be, of course, a number of different problems. So maybe there's a timing issue in the code. Maybe you don't use locks properly. Maybe if some other process does something in a very specific order, a bug appears. So you can solve that problem in different ways. You can, for example, try to write stress tests for your code. Maybe you have a suspicion which part of your code might cause that bug, sometimes, rarely. Maybe you can execute that much more frequently. You can execute it as fast as you can to force that issue to appear. You have to be careful if you try to debug such problems with an interactive debugger, which in general I always recommend, and I know also not every developer does, that interactive debuggers change the timing of your process. They make it slower, typically. So a lot of those timing-related bugs might just disappear and become hard to reproduce. Maybe the bug disappears if you attach an interactive debugger, but maybe it's still there if you just log to a log file instead. So maybe you can get more information about your application out that way. In the worst case, you can wait for the bug to appear, but add code that detects that situation and then tries to diagnose the system, try to dump some status information, like what's the state I am in. And maybe that will help you find the problem. If a bug is only reproducible on some machines, then it's, well, a natural assumption that maybe this has something to do with those machines. So you want to gather all the information about the environment naturally, about the operating system, the CPU, the build numbers of your applications, other applications as well. Anything that could interfere with your program, really. And here, desktop environments are the absolute worst. So there are virus scanners that block access to files. There are system tools that hook all kinds of system functions. System management tools that would disable your software. User rights management that can go wrong. Digital rights management software that also hooks everything. Maybe you can reproduce this environment in a virtual machine. Maybe the client where the bug appears has some kind of imaging mechanism and can image a virtual machine where you can work on. Maybe this doesn't work. Maybe it only works on a machine at the client side. Maybe you can remote desktop into this, or in the worst case, you can have clients ship identical machines to you. We had that as well. And here it is important to keep an open mind and not to focus too soon on some probable cause, because this could still be anything. It could be just that these machines are very slow, very fast, very busy, and it has nothing to do with the environment, really. If everything else fails, then you want something that will automatically report errors, like the bug reporting system I've shown initially, to catch as many similar issues as possible. And maybe you're lucky and you find one of those users who's more helpful than the others. And there are open source solutions to do that, like Google Crashpad, of course. You can, if you're really daring, you can also try to ship analysis code that tries to detect that situation while it happens, and it could report the status of the system back through that bug reporting architecture. If you have really, really, really great error reporting, you can also try out fixes on live applications if the bug only occurs rarely. But we have done this exactly once in a problem we could absolutely not reproduce. We tried out fixes and had the error reporting report back if that worked or if it didn't. And maybe if everything else fails, you can only look at program state after the problem appeared. Maybe you can look at files that have been written by your program with wrong output, and then walk your way back to find out what might have caused this output. So another little quiz. We had a customer report that starting our software failed. And according to log files, there was some bad alloc exception. Now, we could look in our bug reporting database, and we found out that loading the settings file failed for some customers. We couldn't reproduce that, of course, but we could ask the customer to send us his settings file. And indeed, that contained some bogus data. It contained some number formatting strings, and instead of a number formatting marker once, it contained the same marker 2 to the power of 18 times. And it was always a power of 2, I think, which was kind of suspicious. So we thought, well, maybe something doubled that data structure, 18 times. So we looked, what is that data structure? And that data structure was a vector. It was a vector of pairs where the size t is some index into the string, and the format is some string probably, which would be the number format you wanted to insert at that location. Okay, so that data structure has some problems. And now this was stored in shared memory. And it was shared between different processes. Somebody an idea of what the problem could be already? What could make processes disagree on the size, for example, of that thing? Doubling it by loading and saving again.
Vector pushback's not atomic?
Vector pushback's not atomic? No. You mean we wouldn't synchronize them correctly? Yeah. That doesn't sound like doubling, right? Then maybe you get corrupt data in them. But no, they were doubled. The size increased. Like every time we saved, somebody would increase the size.
It got cleared, and so you clear, and then you write everything in, and in between the other process already cleared and wrote its own data in.
Also a good idea, but in that case, I think our mutexes were correct and were not file logs. So how's that vector size computed? So we take the size in bytes, and we divide it by the size of that element in the vector, right? And that size of the vector element contains a size of t. So how big is size t? Is it the same in all processes, necessarily?
No. Hopefully.
No, because I didn't tell you, but we might also have forgotten at that point that we shared that shared memory between 32-bit and 64-bit processes. So using a size t there wasn't such a good idea. But this is something where that we could fix by using int32 or something, or int64. But this is something where we come back to the first part where I said, well, static asserts can really help you find bugs at compile time, because we added the static assert that asserted on all compilations that data structure in shared memory has always a fixed size, regardless of the build setting, architecture, whatever. It has to have, I don't know, 4,000 bytes. That made sure we never made that bug again. Yeah?
Just a question, how could those two machines access that shared data in a safe or in a valid manner? Because they had a different idea of how the data is laid out.
No, I don't think so. If all the other data types have the constant.
Pair of size t.
There was. Oh, yeah, that you mean in that case. Yeah, there was a bit of luck involved that I think one of them was doubling it, and then they all became 0, and 0 was a valid value again, and then that's how that worked. Yeah, there's a bit of luck involved that this ever worked at all, the doubling. Okay, now let's say we have a good reproduction. We get a good handle on our problem. We can analyze it as often as we want. Now we have to find out what the actual bug is. So how do we do this? How do we go back from that reproducible situation to the actual description of the problem that we have to fix? Because usually the symptom that we get, the crash, that is not the bug. The bug happened somewhere else in our code, and it happened earlier, possibly. And we have to walk our way back. How do we find that real problem? So again, we can use all the sanitizers, and we should always use all the sanitizers again in testing. And we should use an interactive debugger wherever that is possible. But there are a lot of other tools that we should know about and possibly regularly use. First of all, especially if you're new, maybe a new code base, maybe it's a part of your application you're not familiar with, you probably want to gain an understanding of the larger system. And you can do this by tracing calls, by trying to figure out who calls what in which order. And this is what people typically did with printf debugging, which I think a lot of people are really big fans of. But printf debugging, so inserting printf statements to trace data, that requires recompilation. And it's a really, really limited technique. It's much better to use tracing breakpoints in all the debuggers. So these are breakpoints that don't interrupt the execution. Well, they may, but they don't have to. But instead, they can just print out data at that point. Messages or local variables, registers, whatever. And they have a lot of advantages. First of all, you don't need to recompile your code when you change your tracing breakpoints. Tracing breakpoints can be added to places where you can't write a printf statement, to operating system functions, for example. Do you want to find out who opens files in your application when it starts up? You can add a tracing breakpoint to create file, for example. You can add them to binary code. And GDB and LDB are incredibly powerful. Visual Studio in that case, not so. You can add arbitrary commands to each of those breakpoints. So for example, you can make it so that that breakpoint not only prints a variable or a register, but it can also print the stack trace of where that happened. So you can get a pretty quick idea of what was called and by whom and in which order, which is often quite a lot of information already. And they can even be scripted, but I have rarely used that with the Python API even. But again, of course, always the warning, adding all this tracing stuff may make timing-dependent bugs disappear. And then, well, you might have to revert back to printf debugging, to be honest. If what you're interested in is specifically the interaction of your program with the operating system, then of course you could add tracing breakpoints to all the operating system functions you're interested in, but they're typically much faster ways because all operating systems come with very good logging tools that log specifically the interaction between your program and the operating system. So in Windows, there's Process Monitor, for example, which can log the registry accesses, file accesses, and what else? I forgot. Network, maybe? These are the two big ones. On macOS, there's dtrace, and on Linux, I think there are a couple of tracing tools that will trace different aspects of your system, depending on what you're interested in. And of course, here it's very important to get a better understanding of your operating system, to get to know the semantics of your operating system objects. So to avoid the bug that I made with the file logs, for example. You should probably know how file logs work, how shared memory works, virtual memory, the file system in general. So this is a part that, of course, takes a bit of time and experience to learn about all that stuff. And then there are a couple of techniques that I have used often to find out, if that turns out to be very hard, what the wrong part of your code is. So maybe you have a state of your code that you know still worked. It didn't have that bug. Maybe you can do a binary search over the changes since then. And Git bisect will help you here. And you find the commit that introduced the problem you're just looking for. And that's very important because with that commit, you're probably trying to achieve something else. So you have to make sure that you don't reintroduce the old problem by fixing the new one. So it's a very good idea to find out what introduced that change, that bug. Look at that change and try to find a solution for both problems. So for the old problem, avoiding the new bug. You can also step through working and broken versions of your code in parallel. If it's completely unclear why they should ever differ, why they should behave differently, you can go over both of them at the same time and find out what's actually different. You can also do the reverse, disable code until the bug disappears, and do some binary search technique, disabling ever smaller portions of your code until you have that line that actually causes that problematic behavior. Both of these techniques require some knowledge of the code base. They require recompilation. They can be super time consuming, or they can be very fast. It is very hard to say that from the start, if that will lead to success. When you're looking at especially older code, a good debugging technique is to improve that code as you go. You're trying to understand what that code does while you're looking for the bug. You're trying to think of invariants that should hold, but maybe didn't, or that weren't documented, but you think they should hold. So maybe you can introduce those asserts that were missing. Maybe those will trigger and tell you much earlier where your code deviates from that path of intended behavior you wanted. You can write complex checks that you wouldn't leave in release builds maybe you just need now for debugging. If you are looking at legacy code, you can also introduce the better programming techniques somebody should have used from the start maybe, while you're trying to understand that code. Smart pointers, etc. And maybe that will fix the problem you're looking for. And maybe it will fix many others that you haven't even reproduced yet. just by using better C++ programming techniques. And then there's a number of tools on Windows and Linux at least that try to do exactly what we are trying to do here, that they record a trace of your application until, let's say, the crash. And then they let you walk backwards through the program execution states. So WinDebug does that. And then there's this undo debugger. There are also frequent sponsors at conferences and give talks. And that can also be a good technique to walk back until you find the situation where your program goes wrong. And here, of course, it's always important, I've already mentioned twice, I think, to use interactive debuggers, to know those tools really well, to know how data breakpoints work. That means breakpoints that will interrupt the execution when you read a specific memory address, or when you write a specific memory address. That can be a super powerful technique. You can customize them by putting functionality into scripts. You should write visualizers for your own data types, for example, so that the debug visualizer can print useful information about data types that you have written. And it's often a good idea if you're, programming, to get at least passive assembler skills, because a lot of the time you will fall back on disassembly code if you're trying to find a bug. So here we have, I think, the last quiz. So we have a very simple problem here. We have some indices, and we call a function that's not a function that we have the source code for. And that function, we pass that array in some C-style way by pointer and size. And we should get a range back of the actual items. But now that fails. We don't get 4 items back, we only get 2 items back. How do we want to find that problem, because at the very least, we can write a bug report and send that to the owner of the library and tell them, hey, there's a bug in your program. How do we find out more about this? Maybe find even the cause. Maybe we can tell them, here's your bug. That would probably speed up the process enormously. So anybody has an idea what we should do? What would be a good next step?
Open up the debugger.
Sorry?
Open up the debugger.
Yes, and then what? Open up the debugger, that's a good first step. And then what? What do we want to find out? Yeah?
You're trying to step into get item from indices.
Yes, you can do that. That's the possibly slow way. It could be a lot of code. It's disassembly. That takes a long time. Yeah.
You might want to see what range actually contains.
Sure. Let's say we check that, and everything that interests us, it's 2 of these indices. Maybe it's item 1 and 7. That is maybe noteworthy, but it doesn't help me really pinpoint the problem. So we could use,
We'll check what type has a range.
Yeah, I removed that here on purpose. Okay. We could use a data breakpoint. If we want to find out where the problematic piece of code is to make a better error report, we could ask the debugger in that case, let us know the point in the program where that pointer we're passing here is red. So that pointer has 4 bytes, that's these 4, and we pass it the pointer. So now the execution will continue, and the debugger will interrupt. And at that piece of code where that array is red, and maybe we learn something more there. So we find something like this. So somebody is reading that array and then is doing some iteration over that array, or over the 4 indices. Unfortunately, this is not what we see, of course. This is what we see. So this is ARM assembler code. Who here is familiar with ARM assembler code? 3 people. Who would be familiar with Intel assembler code? Better, right? Because it's the same for me. I've been reading assembler code for 20 years, but I still can't understand this. So I annotated it. So here, we're getting the pointer P to our array. This is this line. Here we get the loop variable, V. And here we are accessing that array indexed by V. But we're not indexing it by V multiplied by 4. We're indexing it by V multiplied by 8. as if that would be an array of 8-byte size objects. That is clearly wrong. It's also no surprise that it gives us exactly half the items back, because it skips the other half. And it also tells us exactly what the bug was, actually, and that sped up things immensely. Because that code was ported from Windows to macOS. So probably somebody cast that integer pointer to a long pointer, and on Windows they have the same size. But now they recompiled it on macOS, and suddenly long has 8 bytes. And that was wrong. So here, data breakpoints saved us. We could write a very good bug reports, could tell them, here's the bug, and that was fixed very, very quickly. Okay, now we've seen some techniques to go from the report to the reproduction and possibly to finding the actual bug. And we've used quite a lot of we've seen quite a lot of tools to do that. Debuggers, sanitizers, reverse debuggers, logging tools, etc. And we've learned something about the operating system along the way. But there's one crucial technique to debugging without which this will not work. Because most importantly, you have to be able to question your own assumptions. You have programmed something that was wrong. That much we know. If you always assume you did the right thing, then you will never find out what was wrong, right? Okay, now we've found the problem. And we want to fix it. But before we can fix the problem, we can think about the problem and ask, what kind of bug is that? So we can classify it into 2 categories, maybe. There's one category which I would call, you didn't write what you meant, but you didn't quite write what you meant. But it's typically a small problem. Maybe you forgot to initialize some data. Maybe you should have used the smart pointer and didn't, and now you messed up the life cycle of some objects a bit. Or you used the wrong logs. So often this could be fixed by some small change. You introduced that smart pointer you should have used, and everything works. The other kind of bug is, yes, there's a but. The but is, maybe that's a small change, but maybe you've made the same problem in other parts of your code base. So maybe you should look for that. But the other kind of bug is that you wrote what you meant. That means you wrote what you intended to write, but you meant the wrong thing. There was an error in your reasoning. Your mental model was wrong. You have to think again about the problem you're solving. Maybe you need a completely different algorithm. Your approach will never work. Maybe you didn't understand the input data correctly, or the specification of someone else's code you're using. You didn't use the correct operating system facilities, or they just don't do what you thought they would do. Or maybe you just, didn't understand what you actually need to do. So maybe your input data is different from what you think it should be, or your output should be different. So that's a kind of a big bug. You have to really think. You have to go back to the drawing board and, find a better solution, probably. So how can we distinguish those two? That is not so easy. Let's look here. We have some little code sample. We get some vector of pointers. We iterate over that vector and then call a function on those dereferenced pointers. That's not very interesting, but maybe it crashes here. So we get a crash because that pointer is suddenly null. So we can fix this. We can just write an if. Cool, fixed. But is that the right fix? Is that what we should do? What are the questions that we should ask to decide if that's the good fix? So we can do some mock code review. We can ask, where does that come from, that vector of pointers? Who produces that? Why is there null in there? Is that valid that there is null in there, or does that violate some previous invariant? So should that happen or should that not happen? And only then can we decide if that's the correct fix. Yeah, valid, could be one of those pointers could be null, weird as it is, so check for that. Or if we need some completely different algorithm to prevent any of those pointers being null. So, could be good, could be the wrong fix. So, like I just said, we have to look at the bigger picture, ask ourselves what we're trying to achieve, how did we do that, was that the correct approach, or do we need an entirely different approach? And we have to rethink our assumptions and well, find a better solution, maybe. And when we've done that, then we can proceed to fixing the bug. Because now we know, is this a large change, or is this maybe just a small local change? So how do we best fix that bug? And often the advice is that we should find the smallest possible fix that fixes the bug we've just found. Because that smallest fix has the advantage that it has a very low chance of introducing new problems. And that's probably a valid point. The smaller the change, the smaller the chance of new problems appearing. But I don't think that's a very good way of phrasing it, because people will hear the small and not the smallest fix that actually fixes the problem. So you run the risk of fixing maybe only a symptom of the bug. You don't go to the root of the problem. It hides one instance of the bug and doesn't fix the others. And even if it would be maybe a good fix, you run the risk of accumulating small fixes on small fixes, and suddenly over time your code quality degenerates, and at some point you should have stopped and asked yourself, is there a better solution to this that avoids all these small fixes? So I would phrase that differently. I would say you should first ask yourself, given that all you've learned now while you were trying to analyze that bug, you probably understand more than you did a few days ago. How should that problem be solved in the best of worlds? If you had, let's say, infinite time and resources, how should that perfect solution look like? And then you can at least try to move towards this solution. And then you should, only then afterwards, should you ask, okay, back in the real world, given the constraints I actually have, that maybe I need to ship something, I need to ship something to users that have this problem, then you can ask, okay, what's the small change I should do now to satisfy my users or something? And maybe I can do this in the stable branch to get an update out quickly without forgetting what the real solution looked like, and maybe move towards that in the development branch only. And in this way, we can make sure that we get fixes out quickly without reducing the quality of our code over time. When we have fixed the bug, then we have to ask ourselves, how could that happen? Was it maybe too hard to program incorrectly in our code base? Didn't we have some tools that we should have had that would have made it easier to do the right thing? Did we miss some library, some helper function that could have avoided that problem? Maybe an algorithm that, well, I tried to write myself, but well, that didn't do that very well. Or just some general programming practice that we should introduce. And then we can maybe prevent that from ever happening again. Because, well, nothing is worse than making the same mistake over and over again. Can we at least fix that bug somewhere else in our code? Can we look for the same pattern in our code base and fix it everywhere? Or can we even go further and introduce some abstraction that was missing that would have helped us and maybe helps others in our code base because we have the same problem somewhere else in our code base? And this can mean very different things. So it can mean algorithms. So this is something I mentioned yesterday already in another talk. This is something we had surprisingly often in our code. So here we have some vector of things, integers in that case. But it doesn't have to be integers, it's for simplicity here. Then we sort it. That takes a less predicate. And then we want to get the range of unique elements. But that unique algorithm takes a different predicate. It takes an equal. So the problem that might occur here is if somebody does that, and they don't have ints, but maybe more complicated objects with custom comparators, that suddenly these two comparators are not compatible. They write an equal and an less that are not compatible with each other, and suddenly this is wrong. When we had this pattern We have 1 million lines of code maybe. We had this 74 times in our code, which I think is surprisingly large number. And well, the solution was, of course, to introduce some abstraction, some algorithm in our library that does exactly that. It does a sort and a unique and well, gives out the range of unique elements. But it only takes one predicate and creates the other predicate out of that less predicate. So the two are always compatible, avoiding that bug. So that's introducing algorithms that maybe you didn't have. Error handling is another such case. Error handling can be super tedious. Here, I'm trying to open a file on a POSIX platform. So, and there are so many cases. You open a file. If it succeeds, it returns a non-negative value. Okay. It might return -1, I think, and interrupt. And then you have to try again. Okay. And then there are a couple of others. The permissions are wrong, the file doesn't exist. These are the errors I want to allow. I know they can happen. So in this case, I'm fine, and I will just return without a file. And then there are all the other ones. EIO, where I never know, when will that happen? And what should I do if that happens? I don't know. I want to get a bug report. So here, this is how it looks in our code base, how we can encode all of that information, in a more or less straightforward manner to say, okay, the success case is the return value is non-negative. Interrupt and invalid is retry, and invalid file handler, and all the other ones are allowed. Everything else, please report. And the same holds on Windows, where it's maybe a bit easier, but a lot of API functions on Windows return 0 when there's an error, and then you have to call getLastError to ask what the error actually is, and you want to report that. And all of that can also be wrapped in simpler error handling macros or functions in that case. Okay, and now we are almost done, and the last thing we have to do is like deliver that fix, implement it, commit it. And there are a couple of things that hopefully everybody already does. So we want to document it. We want to tell other developers why we did what we did in the code, ideally, so it doesn't rot as quickly. We maybe don't want to only document why we did something, but I think a very important information that we should put into the code, especially maybe if we implement a weird workaround or something, is when can we remove this? Or in other words, the next developer will ask, do I still need this? Or can I remove this now? So that's also an important information that you should put into those comments. Then code reviews. Who here does code reviews as part of their normal development cycle? Good, that's much more than address sanitizer. Very good. Cool. Who does pair programming? Also nice. Cool. Okay, and often it becomes pretty obvious, right, that you made a mistake once you explain it to somebody else, right? That's, I think, the killer feature of code reviews is not that somebody looks at my code, it's that I have to explain it. And then I notice, oh, that doesn't sound so good. Version control, I think that everybody does. Who doesn't do version control? Nobody dares. If I phrase it that way, nobody will say. We want to separate the changes to functionality from commits that maybe are only refactorings. We do that. Of course, you want to submit small changes, as small as possible, that they still make sense in and of themselves. So nobody wants to review 3,000 lines of changes. And as I've mentioned, refactor code while you're debugging it, because you already understand it. So you're in a good place to improve it as well. And then last but not least, we might want to write a test to avoid the same issue from appearing, to make our software more robust, of course. Also something hopefully everybody does. Who writes tests? I'll phrase it that way. Yeah. And I think the killer feature here is if you have cases where you can not only test a few cases, and then these are the ones that work exactly, but all the other ones doesn't, but when you can write test cases for random input, right? And then you can be really sure. Yeah.
Doesn't doing a refactor while you're fixing a bug increase the likelihood that you'll introduce a new issue while trying to fix the bug?
Yeah, but that's true for every change we make, right? I mean, it could be, well, you should probably do it separately so you don't mess up your debugging, but you could do it in another branch and commit later. But that could also mean just writing more asserts, right? To maybe narrow down the problems, yeah.
I guess that'll be the point of writing new test cases.
Sorry?
I guess that'll be the point of writing the new test cases.
Writing new test cases afterwards, so you didn't make something worse. But if you don't do refactors because you're afraid you'll introduce another problem, then we'll never move ahead, right?
Sure. The concern is more if you introduce a new problem because you did a refactor along with the bug fix, and then you have to back it out to.
Yeah, you should separate those,
yeah.
and maybe do that in a separate branch and not complicate your things any further. Yes. And with that, we are then done, and we have hopefully made our software better, prevented the bug from reappearing, and architectured our software engineering process in a way that reduces the number of bugs remaining. And yeah, that's now I'm open for more questions if you have, or horror stories of your favorite bugs.
When you say test with random input, do you really mean random or just arbitrary but non-random input? Because with random input, you don't have a reproducible test.
That is true, but it's so it's something we do maybe for basic data structures where you where maybe there are different cases, but I mean you can imagine data structures where if you call stuff in a certain sequence, you might end up in like corrupting your data structure. In that case, maybe the history is not so important. You only need the previous step and the operation you did, right? That would be enough to recreate the problem. But in those cases, doing a large number of random tests can be super helpful because they might find issues you haven't even thought about. If there are, that only works if you can have a simple verification algorithm. So if maybe you have a very simple, inefficient way to implement the same result that you can then compare against, right? You have your super efficient tree, blah, 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 or you have an array where you always overwrite everything and it's hard to get wrong, but it is super slow, but for the test, it doesn't matter. Yeah.
Most test frameworks will let you have random input, but then save the seeds. You can reproduce that.
For example, but then they will probably not make sure that there are so many parameters. Maybe you want to have a very narrow range of data, so you create a lot of overlaps, or you want the opposite and use like the entire integer range. So there are so many variables to that, right? Here was a question? No? Any other question? Any bug you want to share that was amusing or horrible? Okay. Then, I thank you for your attention. I'm here the rest of the week if you have any other questions or comments. Thank you.